net change or rate problems. So these are problems where they give you one or two rates, and then you have to find the accumulation of things or the rate at a certain time, right? Typically, they like to give you two rates here, like in this case. Tide removes sand from a beach. So this one is the out. So usually one is an out, or it's removing stuff, and one's adding stuff. Commutation adds sand to the beach. That's the in. So a couple things to keep in mind. Anytime you want to find the total, this is only for the total amount. Again, total amount at any time. You want to make up your own equation. It's like an a of x equals the initial value. In this case, that'd be 2,500 cubic yards plus the integral of the in minus the integral of the out. When you do the integral of the in, look at notice my domain here is 0 to 6. I'm going to go 0 to x though, right? Because you don't know when we're stopping. Same with the out, 0 to x. And again, these could change. Sometimes they'll say, oh, we only pumped for the last 2 hours, so this would be like 4 to 6 or something. So you want to actually read the problem when you do stuff like this. So if you want to find a total amount, that's how you do it. And that's how and you need to do this if you need to find the max or min. So if you need to find the max and min, you have to write the total amount first, and then you can take the derivative, which is basically just in minus out, set equal to 0, and do the rest. So just keep that in mind. If I'm trying to compare those two, is there more incoming or more outgoing? All you do is compare R of the value versus S of the value. Which one has more? Whichever one has more, that's what's happening. If you want to find out the amount added or subtracted, right, during a time frame, during A to B. So just the amount added, subtract, no total amount. Then you just integrate with everything we're talking about from those times. Added in, minus out, right? You do not add the initial value. So little things like that you want to keep in mind. So this is how we do net change problems here. So let's do a couple. This is the first one. This one actually only has one equation here. The rate of change of the number of mosquitoes on a tropical island at time t days is multiplied by this. So that's, again, this is the number of mosquitoes. You want to keep in mind what the rate is. There are 1,000 mosquitoes on a tropical island at time 0. So it's my initial value. Show the number of mosquitoes is increasing at time c. So keep in mind it's the rate of change of mosquitoes. So here, a lot of people think, oh, I gotta take a derivative. We're already a rate though. R is my rate. So all I gotta do for A is do R of 6. Put that in my calculator and see what I get. Now it's increasing, so I probably should get a positive number. So you just show what that is. Again, you can use your calculator on this. Show that the number of mosquitoes is increasing. That's what R is. This is the rate of mosquitoes. So you plug it in. If you get a positive, it's increasing, and negative, it's decreasing. That's it for A. B. At time 6, is the number of mosquitoes increasing at an increasing rate, or the number of mosquitoes increasing at a decreasing rate? So notice how it's talking about, is the rate increasing? So our rate is R. Is that thing increasing? Well, increasing, decreasing in general has to do with the derivative. Since we're already a rate, that's why on the first one, I didn't need to take a derivative because we're already increasing, decreasing. Now I'm asking, is my rate increasing? So I got to take a derivative of R. Plug that into your calculator. You get a positive, it's increasing. You get a negative, it's decreasing. Right? Since we're a rate of a rate is a derivative. Since we're a rate, the first one's not. According to the model, how many mosquitoes will be on the island at time 31? So here's the key thing with this one. Notice how many mosquitoes will be on the island at time 31? So that's a total amount of mosquitoes. So my equation for that one is going to be the initial value plus the integral of my mosquitoes are from 0 to 31. Right? So according to the model, how many mosquitoes will be on the island at t equals 31? That's a total amount. So we're going to add the initial value to that. And then you get some answer. D, to the nearest whole number, what is the maximum amount of mosquitoes on the island from 0 to 31? Show that analysis to conclusion. So anytime we want you to find the max or min, we always do the same thing. It's an absolute max min problem. So we're going to have to set the derivative equal to 0. We have to find critical points and endpoints. To find the critical point, I'll go ahead myself. You can set the derivative equal to 0. To find those critical points. To find the endpoints, they already gave it to you. It's 0 and 31. Once you find those two things, once you have my values here, which I already have over here actually, I want to see what the max amount is. So anytime you want to do absolute minimum max, you're going to plug these values into the original equation, or total equation, I should say. So once I get my critical points and my endpoints, I'm going to plug those back into the total equation. So what I mean by that, I'm assuming we're going to plug it back into this equation to find our total. So let's say a of x to my total, right? And that's the initial value plus the number, the integral of the rate of RT. So for let's say 0, 1. Let's do the endpoints first, right? So a of 0 would be the initial value, which I think was 1,000 mosquitoes, plus integral from 0 to 0 of R of t, which should just be 1,000. A of 31, we actually already did that. We did that up here. So it'd be 1,000 plus the integral from 0 to 31 of RT. Whatever my answer is up there, it's the same thing down here. And then you try your critical points. And then if you get a critical point, let's say my critical point, I'm just going to make one up. 3.12671. Right, you can either store that value and say lowercase b equals it, or you can just keep as many decimals as you can. It's fine either way. So if I do a of, let's say b, because I store my value, so it's me 1,000 plus the integral from 0 to b RT equals, get that value. Whichever one's the highest is your max. And what do they want here? So they're going to tell me what is the maximum number of mosquitoes. So they wanted the number of mosquitoes. So your answer would literally be whatever the max is, whichever one of these is the max. And they want to round to the nearest mosquito. There you go. Let's do another one. Just make sure we have this kind of idea down. This is from 2004 test. Traffic flow is defined as the rate at which cars pass through an intersection. Measured in cars per minute, the traffic flow in a particular intersection is modeled by the function f. So here's our function f. That's the traffic flow model. So again, it's the rate of cars coming into this intersection. A, to the nearest whole number. How many cars pass through the intersection over a 30-minute interval? Over a 30-minute period. So all we're going to do is integrate from 0 to 30 of f. Right? It said how many, so I have to integrate the time period. B, is traffic flow increasing or decreasing at time 7? Now, so you got to watch it here. This is my traffic flow. So it's asking, is that increasing or decreasing? So that means we are going to take a derivative of that guy. Right? Sometimes you don't take a derivative. It depends on how they say it. They're pointing out the traffic flow. Like, hey, there's my traffic flow. Is that increasing or decreasing? Well, the way you find increasing, you take the derivative of that thing. So I can do f prime. You just put that in your calculator at 7. So f prime was 7. And whenever you get your answer, right? Positive is increasing, negative decreasing. C, what is the average value of traffic flow over a time interval? So very key word right there, average value. The way we do average value never changes. You integrate the thing you're talking about, and then you divide by the subtraction of the limits, the difference between the limits, like that. So in this case, we're going from 10 to 15. So we're going to integrate from 10 to 15 of f of x, our function, f of t, I guess. And we're going to subtract off 15 minus 10, which is 5. And whatever value you get is the average value. Units of measure, let's talk about that real quick. So we're integrating f of x. This guy right here, it says it right here, measured in cars per minute. So cars per minute. So when I got this answer here, this would just be cars. Because when you integrate, you go up, you lose it. So in general, guys, with units, right? When you integrate, you lose the base, lose the denominator. When you take a derivative, you gain a denominator. So like I'm at cars per minute, I integrate that, I'm gonna lose that thing because you're gonna multiply and stuff like that. So you just get cars. Over here, I was at cars per minute originally. That's my f is originally cars per minute. By divide, I took the derivative, so I'm gonna gain another thing. So it's cars per minute squared. All it is. Look at this one. I'm integrating, so I get cars. But I divided by my time. right? And my time here was minutes. 1 over minute. So I'm going to get cars per minute. And that's how that works. I just keep that in mind. So with units, right, anytime you integrate, you go up, you're going to lose the denominator. Anytime you take a derivative, you're going to gain a denominator. That's all it is. And let's talk about D. Another key term one. What is the average rate of change? Average rate of change is another key term. That's the slope, but like the old school way. Old school slope. That's y2 minus y1 over x2 minus x1, also known as like f of f2 minus f of x1. Right, so average rate of change is always this like the old school slope. Average value is always this integral right here. So they want me to find old school rate of change with 10 for t between 10 and 15. So I'm going to go f of 15 minus f of 10 over 15 minus 10. Like that. And then you can plug that in your calculator, you get an answer, blah, blah. Indicate units of measure again. So let's talk about the units of measure on this one. Kind of like the last one. It should be, kind of be the same thing. F by itself up here is cars per minute. They told it right there, cars per minute. So I have cars per minute on top. On the bottom, it's time. So you're dividing by time. So cars per minute over time, cars per minute squared. That's all it is. Let's go over one more. One with the 2 equations. So right here, it's from 2002. The rate at which people enter amusement park is given by this. So this is people entering the park. So that's our added value plus. People exiting park, leaving it, is our L. So it's people leaving. So right, this is in, this is out. Probably should have wrote that instead. Anyway, live and learn. Both E and L are measured in people per hour, so keep that in mind. This is people per hour. And T is measured in hours after midnight. So these functions are valid from 9 and 23, the hours of which the park is open. At time 9, there's no people in the park. So my initial value at 9, it's 0. So my initial value is 0. How many people have entered the park by 5 p.m.? Now notice the question, it's only entered the park. Not how many total people are at the park, it's just entered. So for that one, I'm only going to integrate the entered one, E. So I'm going to integrate E of t dt from 5 p.m. they calculate 17. So from, notice again where it starts. We start at 9, not 0. So 9 to 5, 17. Plug that into your calculator, get an answer. Round to the nearest whole number. Now again, so once you get around to the nearest whole number, if you cut by units, right, we have people per hour, but we're integrating, so we're getting rid of that hour, so it's people. B. The price of admission to the park is 15 until 5 p.m. After 5 p.m., the price of admission is 11. How many dollars are collected from the park on a given day? So from opening to 5 p.m., it's only 15 bucks. So the integral we just did, we're going to run that back. Minus 17, E of t dt. But now we know it costs $5. So all the money we're making, we're going to times that by 5. $15, sorry. And then they change it. After 5 p.m., it reduces to 11 bucks. So now we're going to go 17 again because it's 5 p.m. Multiply that by 11. When does the park close? Go back up top, so your domain at 23 hours or 11 p.m. So we're going to go to 23. Right? And you get some answer. You just get people again. That's all it is, right? Again, we're only talking about entering the park. So we enter from there, break it up since there's 2 different values from there to there. That's it. C. Let H be this thing for 9 and 10. So H is like the total amount. Now remember, we generally add the initial value, but the initial value is 0 in this case. So this is a total amount. The value of H of 7 is the nearest whole number is 3725. Find the value of H prime of 7 and explain the meaning of H7 and H prime of 7 in the context of the park. So H of 7, let's get that out of the way first. H of 17, why do I keep on leaving out the whole number? H of 17, since H of 17 is the integral from in minus the integral of out, from 9 to 17. That's the total people in the park, right? When you do plus minus out, it's the total amount of people in the park. At 17, which is 5 p.m. That's all that is, right? So h of 7 is the total amount of people in the park. And then h prime of 17. Well, let's figure out what h prime is first. So we're gonna take a derivative of this. Actually, let's go back up here to the equation they gave us. They want to take a derivative of that guy. Remember, derivative and integral cancel each other out. So all you're gonna get is ex minus lx. When we plug in 17, we're gonna get e of 17 minus L of 17. Now, remember E and L, let's go to the units, right? E and L are people per hour. So the answer you get is going to be in people per hour. So that means it's a rate, right? In general, it's a derivative. So like, right, let's look at what the thing we're taking a derivative of. This is the number of people in the park. So we took a derivative of that. So remember, derivative means increasing, decreasing. So anytime you take a derivative, you're going to increase or you're going to decrease if you're positive or negative. So all this means is the number of people in the park it depends if it's increasing or decreasing, if you get a positive or negative. So remember, you have to plug these values in your calculator to get an answer. I believe this answer is actually negative when you plug it in. So the number of people at the park is decreasing at t equals 17 or at 5 p.m. Either one's fine. So that's what's going on there, right? H is our total amount of people in the park. You took a derivative, so that means you're talking about increasing or decreasing, and it all depends on what sign you get. So that's C. D. At what time t for n between for t between n and 23 does the model predict the number of people is at a maximum, right? So again, at a maximum, we do this a lot. If you want to find the maximum, you have to find the critical points plus endpoints. I have the endpoints 9 and 23. Critical points, you got to take the derivative set equal to 0. Now we have the derivative right there. So we're going to set ex minus lx equal to 0. Right, now there's two ways to solve it. I'm actually going to put these in my calculator so you can see it. Let's do this real quick. So here it is, movie magic, it's all typed in. Now there's two ways to solve it. I want to find out where, when I subtract them, it equals 0, or where they intersect. Now sometimes you just find where they intersect, like in this case. Before I graph it, you should fix the window, 9 to 23 on your x, or your t. Right? But in this case, if I graph, I'm not going to see the intersection. Like these are high numbers, so I would have to fix my window even higher, to move it up, change it to something like, oh, my y, I probably have to go all the way up to, what is that, 16,000, so I could see anything. So there's the first one, and there's a second one. So they intersect right there. So I could do that if I'm good with my calculator. Change the window. Apparently 16,000 is a little too high. Let me go a little lower. Maybe just like looks like a 10,000 maybe. That's probably still think it's way too high. See a little bit better though. So you can do that. I can see it better. Find intersection. Second calculator intersects. Just move it till you get kind of close to it. Kind of hard to see here. And I get that. So 15.79 is where they intersect. That's my critical point. Now again, you can either copy that all down and just use that. That would work. Or you could store it. The way you store it, if you want to, second quit. Go select your answer, the one you just found. Hit store. And then select a variable. Select A. And now it's stored on A. So if I wanted to go back to like integrate one of these guys, all I have to do is go math 9. Select the number I'm starting at, I guess 9. Then here I can just select A. And if you want to pick a specific variable, a specific equation, you can press alpha F4, bring up your y1s or y2s and select the variable. Like that. So that's how the way you could have done a couple of early ones. Another way to do this, the graphing on here, if you don't want to do it that way, you could always just go here to y3, select alpha F4, select y1 minus y3, y2, sorry. Right, to write down this exact equation right here we have. And then you probably want to deselect these guys. So click this and click this so that you don't see them. So to confuse your graph. Probably could fix my window back to negative 1010. Don't want to overkill this. Hit graph, and all you have to do now is find the x-intercepts. And you see it right there. So that's the exact same point we're just going to find. So second calculator, 0. Now here it's kind of hard to see where I'm at. The x tells you you're at 15. So if you just come moving, you'll eventually see it at some point. And then you get your answer. You gotta, my calculator wugged out on me. But that's how you get it. You just go for 15 something. And then we do what we always do. Right? I think it was like 15 point. Oh, in my case, I put for A. So you get, again, if you use that, if you say A, you actually have to say what A is. So write down A equals 15, whatever. And then you can use your correct point A. And all we're going to do is check which was the max. So we have to go back to our total equation. Right there and plug them all in. So you're going to have h of 9, which is the initial value, which in this case was 0, plus incoming 9 and 9, minus outgoing 9 and 9. Then you can have h of 23. Right, so initial value, which was 0, 9 to 23, minus outgoing 9 to 23. I forgot what the equations were. Then you can have h of a, which you could write like this as long as you tell me what a is. Right, so the initial value plus integral from 9 to a minus the integral from 9 to a of out and in. Whichever one is your highest value is your max. And let me add one more question I don't see on here, which they ask a lot. So like there'll be a question E that says, is the amount of people in the park increasing or decreasing at, let's say t equals 12. Right, so increasing, decreasing. So you're thinking, oh, it's a derivative. But remember, increasing by itself is just a rate. That's all it is. And the values they gave us are rates. And people entering, people leaving. So if you want to know if the amount of people in the park is increasing, decreasing, you just want to see, compare the amount of people entering the park at 12, bigger, less than the amount of people leaving the park at 12. Right, you just compare these two. Whatever one's bigger wins, and that's, so if this one's bigger, then it's decreasing. If this one's bigger, then it's increasing. That's all you do. And that's net change.